Okay, so today I want to talk about how to turn a min priority queue into a max priority queue. The next topic I want to talk about is turning a min priority queue into a we can say it in other words, transforming a min priority queue into a max priority queue. So a problem we often face in many programming languages, that in most of programming languages, within their standard libraries of built-in data structures, they only provide a min priority queue, which sorts by smallest elements first. But sometimes, in many solutions and in many problems, we have to implement a max priority queue. We need to use a max priority queue. Okay, so since elements in a priority queue are comparable, they must be comparable, or else we won't build a min heap. They implement some sort of comparable interface, and a hack or a trick we can use to implement priority queue. We can simply negate the numbers, the interface, to achieve a max heap. So we can just negate this interface or every number. So now let's look at some particular examples. The examples I'll demonstrate now on the slides. So let's suppose that we have a priority queue consisting of the elements on the right of this slide, of this screen, and these are all in a min priority queue. And also let x and y be numbers in the priority queue. For a min priority queue, if x is less or equal than y, then x comes before y in the priority queue. So the negation of this is if x is greater or equal to y, then y comes out before x. So a lot of people may wonder that why we say that the negation of x is less or equal than y isn't just x is greater than y. By the way, for comparators, if we have the equation if x is equal to y, whether or not the comparator is negated, x should still equal y. Let's see how we can pull all the elements out of this priority queue on the right side of the screen with negated comparator. So first, we negate 13 as it is the greatest element. Then 11, 7, 5, 3, and 2. And there is also an alternative method to negate numbers, to pull the numbers to turn the min priority queue into a max priority queue. So that is, just negate the numbers as we insert them into the priority queue, and negate them again where they are taken out or when they are removed. So when we're inserting elements into the priority queue, we're negating them and negating them again where they're taken out. So that has the same effect as negating the comparator with the comparator. Negating the comparator, yeah. Now let's negate all the elements in our priority queue on the right, and we can see that the smallest element here is definitely negative 13, so it should come first in built-in library, in built-in data structure. They mean heap. In most languages, the built-in data structure is a min heap, and if we add 13, negative 13, negative 13 should come out first. And indeed it does. And the trick here is we do not forget to re-negate the values once they're removed. And next is minus 11 or negative 11, which in fact positive 11 is a positive 11. And so on. Negative 7 is, by the way, 7, and then we have 5, negative 5 or 5, and negative 3 and negative 2. Okay, so that is how we can do it with numbers, that we can negate simply, very simply, by negating the comparator, or the by negating the numbers as they are added. So now let's look for strings. So now, for example, lax is a comparator for strings. Now this time for strings, and last time it was for numbers, and now for strings. So it sorts strings in lexicographical order, and by the way, that is the default way of sorting elements in most programming languages. They utilize the lexicographic order to sort strings. So, for example, if S1 is less than S2, and okay, so let S1 and S2 be strings. So here, if S1 is greater than S2, so this equation. So here, if S1 is greater than S2, then lax of S1 and S2 is negative 1, because S1 is less than S2. And now, let's suppose that the let and lax be the negation of lax. And so here, the negation of lax here is positive 1. In this case, that is equal to positive 5, or positive 1. Sorry. So now we can use lax to sort a string lexicographically. But if we're interested in negating lax, so negating lax that means that longer strings appears before shorter strings, and also that strings with letter at the end of the alphabet appears before those containing letters at the beginning of the alphabet. And this, by the way, would turn the min per heap transform our default built-in min heap into a max heap. Okay, now let's look at the example of turning min priority queue consists of strings into the in this time we're using lax comparator, and by adding all these strings on the right to the priority queue with this comparator with lax comparator, we obtain the following. First, we're pol A, then B, F, Z, X, XR, and then XX, or double X. And by adding these strings on the right to the strings on the right that are in the priority queue that we're taken as the example, with and lax comparator, that is the negated lax comparator, we obtain the opposite thing. We obtain the following: polling of the elements but that is the opposite to the previous. So firstly, we are calling XX, double X, XR, X, FZ, B, and A. So we can see here that we are getting what we wanted to get. So here we wanted to turn a min priority queue into a max priority queue. So if the min priority queue is built in, for example, and we can use it in the default, in the standard library, by using the negated comparator, we can turn it into a max priority queue, which was the goal, or which was the target here. So that's it for my today talk. It was shorter than previous because this topic is a bit smaller. How to turn min priority queue into a max priority queue. Yeah.
Okay. No, it's a good
But
talk. Yeah, no,
thank
it's
you.
clear. No, it's clear what you